Hello, my name is Juan Miguel Castillo from the University of Alicante, and today I'm going to talk about our research project, an RGBD-based framework for automatic measurement of the human body applied to dietetic treatments. This presentation will be divided into 5 sections. On the first one, I will introduce the main motivation and aims of this project. On the second section, I will explain the acquisition process and the 3D model generation. On the third section, I will explain the measurement methods that have been used. On the fourth section, I will show you the comparative results of the measurement methods and the error levels in order to know their accuracy. On the last section, I will summarize the achievements of this project and the future research lines. Nowadays, dietitians and doctors still use traditional measurement techniques to know the fat percentage of the human body. The aim of this work is the creation of a system for the acquisition of virtual 3D models of people under dietetic treatments. Moreover, this system must allow us to take different measures, such as perimeter, area, and volume. As you can see in the image, for the acquisition system, we have a cabin where we have distributed a network of RGBD cameras on different corners. We can also see in the image a green cube, which is used for the calibration of the cameras. From the moment the patient enters the cabin until the model is obtained, it goes through the next stages: acquisition, pre-processing, registration, mesh generation, and texture projection. During the acquisition, each camera captures a point cloud with a color image and stores them. In the pre-processing, different algorithms are applied to the previously obtained point clouds in order to reduce noise and eliminate unwanted parts. In the registry, we have to apply a different transformation matrix to each point cloud in order to align them in a single 3D coordinate system, and then we will unify all them into one point cloud. In order to generate the mesh, the Poisson algorithm is applied to the previous point cloud. Finally, the color images taken by each camera are projected onto the mesh, giving you the final model. This one we show is an example of a model generated with the system we have developed. It is a model quite faithful to the reality, that it's allowing us to monitor the evolution in different patterns both in 3D comparisons and in virtual reality. A user interface was created using Unity 3D, where medical specialists will be able to view the models and obtain the measurements. We are using the ray simulation method offered by Unity for the measure estimations. This method allows us to simulate the cast of a ray from a point in a specific direction, allowing us to obtain the collision points with the other objects. Using this tool, we can easily obtain the perimeter. We only need a circumference that intersects the model and cast rays against the center while we orbit over it. The perimeter will be the accumulation of distances between each collision. In order to obtain the area, this same technique has been used, but now the center of the circumference serves as a pivot to create different triangles together with the collisions and accumulate the areas of these to estimate the total area of the section. To estimate the volume, the circumference is converted into a cylinder and the calculation of the area is applied every 1 centimeter of distance, thus obtaining the volume of the section intersected by the cylinder. As mentioned above, a user interface has been created for specialists where different measurements can be taken. As you can see in the video, you can move the circumference to select the body part to be measured. It's possible to resize and change the orientation of the circle to arrive to parts like the arm. You can also change the height of the circumference to obtain the volume. In order to quantify the precision of this system, we have carried out two types of experimentation. In the first experimentation, we have created different synthetic models using Blender, and we have measured them to know the error of the measuring algorithms. In the second experimentation, we have taken measurements using models scanned by our framework in order to know the whole system accuracy. In the synthetic measurements, we have measured the objects by launching different amounts of rays: 100, 1000, 10,000, and 100,000. For the perimeter, the relative error levels are quite low, and as we can see, the error decreases as we increase the number of rays until 100,000, where they return to increase. For the area, the same configuration has been used. As you can see, follows it the same progress as the perimeter. The accuracy increases up to get to 10,000 rays and come back down with 100,000. This may be because with a very high amount of rays, the distances obtained on each calculation will be very tiny, causing a decimal truncation. Using the same configuration for the volume, we see a different progress. The error decreases with 1000 rays, increases slightly with 10,000, and decreases again with 100,000. But, as we can see in the error levels of each model separately, different patterns are followed. This may be due to the influence of the model's shape and size on the accuracy of the method. In experimentation with real models, measurements of a cube and different parts of the body, head, arm, and abdomen have been taken. As we can see, the relative error in the perimeter is 0.0036, in the area of 0.011, and in the volume of 0.012. After the different experiments, we can say that we have a precise system with an error of around 2.4 millimeters, which could be brought down if we continue to improve the acquisition system. This system can be very useful because of its applications in detecting treatments. It will allow specialists to take different measures and observe the morphological evolution of patients over time. In the name of the whole team I'm representing, thanks for your attention.